Good afternoon, and welcome to the webinar, Maximizing Movement of Powders While Minimizing Dust Exposure with Properly Designed Pneumatic Conveying Components and Systems. My name is Jim Colari. I'm the Editorial Director of Plastics Technology Magazine, and I will be your moderator this afternoon. Our presenter is David Kennedy from VacuumMax. As Business Development Manager for VacuumMax's Pneumatic Conveying Division and Industrial Vacuum Cleaning Division, David's 24-year career began as Sales Manager for the VacuumMax's Industrial Vacuum Cleaning Division, with sales tripling during his tenure. Before joining VacuumMax, David's experience included filtration and industrial equipment sales to the chemical, petrochemical, food, pharmaceutical, municipal, ceramic, and construction industries. Please feel free to ask questions at any point during David's presentation. Simply detach the questions pane from the panel on the right-hand side of your screen and type in your questions. We will get to as many questions as time follows after Dave's talk. It's now my pleasure to turn the webinar over to David Kennedy of VacuumMax.
Good afternoon to everyone on the East Coast and the Midwest. Good morning to those on the West Coast. Welcome to our webinar with Plastics Technology. Today we're going to talk about vacuum conveying, pneumatic conveying powders, a particular emphasis in the plastics industry. So I hope that it will be enjoyable and educational for those who are listening. I'd like to start off on a light note. For my age group, you might remember a movie from the 70s called National Lampoon's Vacation. And it's not unlike pneumatic conveying, where they have a starting point and they need to get to a destination. And if you're not careful, a lot of hazards and difficulties can happen along the way. And that's really the point of our discussion today, is to try to avoid those decisions that make life more difficult. For those who are younger, we went with the GPS icon, the location, the Google icon, that this is where we begin. The basic principle of a vacuum conveying system is that powders are transferred from point A to point B, or granules, from various types of containers, bulk material sources, to a destination using a process of vacuum, that is negative pressure. One of the great advantages of vacuum conveying is that it does control dust. And in the plastics industry, this is a safety issue related to hazardous or combustible dust. And it's also related to a quality control factor. Vacuum conveying controls dust by eliminating hand scooping, which may be at a pilot stage, or it may be at an early production stage in a plant before it starts growing. If there is a leak in a vacuum conveying system, it leaks inward, unlike a positive pressure system, which leaks outward. When you're handling materials that are potentially combustible dust, vacuum conveying is preferred by NFPA over positive pressure conveying for that simple reason. It does deliver the powder to in a closed process from point A to point B. There are, under normal working conditions and in good operating condition, a vacuum conveying system gets it from point A to point B without dust, fugitive dust. It also discharges the material under control or with control. And it also allows you to work with larger containers, such as bulk bags, tote boxes, rail cars, silos, and the like, without having to have a lot of manual intervention, which has the opportunity of generating dust at the pickup points. For the most part, we're talking about dilute phase vacuum conveying, where you can see from that graphic that there is a material is traveling in an airstream, and there is a fair amount of air along with the product. The typical rate for a vacuum conveying system in dilute phase might go up to 25,000 pounds an hour. And in general, the conveying distance is less than 300 feet or 90 meters. And commonly in this part of the industry, up to about a 6-inch diameter convey line is about the maximum size. And then there are all of the rates and line sizes and distances all the way down to the minimum, which would be, we would call up and in, at small rates of 1/4 of a cubic foot per minute, and convey line sizes that might be 1 1/4 inches in diameter on the small end. Designing a pneumatic conveying system, there are 10 identifiable characteristics. There's probably a lot of A, B's, and C's in that list, but in general, we've identified 10 main concerns when you're designing a vacuum conveying system. First thing is to know the powder or the material that you are conveying. The first thing you start off with is a bulk density, which is typically described in pounds per cubic foot or grams per cubic centimeter. It is a factor in calculating the size of the vacuum receiver. Lighter weight powders need larger receivers in order to fall out of the airstream. And it's also a factor in calculating the size of the vacuum producer, which in turn determines the conveying velocity. Higher density materials require a faster transport velocity. You need to know your conveying distance, which comprises of a horizontal and a vertical factor. I mentioned before up and in, which is essentially just a vertical lift from floor level up to a receiver over an extruder or a loss and weight feeder. You need to know the number of 45 or 90 degree sweep elbows, and sweep in general refers to a large centerline radius, 8 or 10 times the diameter of the tube itself. Keep in mind that one sweep, one elbow is the equivalent of 20 feet, up to 20 feet of linear tubing. So reducing the number of elbows is an important goal. Powders do not flow like liquids, and they do care if there are back-to-back elbows. They do care if there are 5 elbows instead of 1. So reducing the number of elbows is important, keeping it to a minimum. So adding taking a 20-foot vertical and a 20-foot horizontal run with 2 90-degree elbows, for example, it's not 20 plus 20 being 40 feet. It's actually 20 plus 20 plus 20 and 20 again for the 2 elbows, for an equivalent feet of 80 feet instead of 40. If you're vacuuming in vertical legs, if there are generally more than 12 or 15 feet of vertical run, if you're running a batch system, material in that line will stop conveying and fall back down. So that's why I say beware of avalanches. If you have that kind of a condition, you need to make sure that there's a line clearing valve to make sure that that vertical leg is cleared before the batch process stops. The convey rate. How many pounds an hour or kilos an hour will be conveyed? Is it a batch operation or is it a continuous operation? An example listed here, if you want to convey 2,000 pounds an hour, but the way your batch process is set up, you need that 2,000 pounds in a 5-minute span. The actual convey rate is 24,000 pounds an hour. This is the difference between 2,000 pounds an hour in 5 minutes versus 2,000 pounds over a 60-minute period. So you need to know the demands of your process in order to properly size the system to determine the convey rate. The material characteristics in the plastics industries, there's lots of different particle shapes and sizes. Powder, pastilles, pellets, flakes, granules. It's important to understand the particle size and the distribution. This is very important in the sizing of the filter system, and also to know whether you're trying to maintain a mixture of products when it's being discharged. This is a mass flow versus funnel flow question. Is the material free flowing? Does it absorb moisture in the process? Is the plant environment temperature controlled or environmentally controlled? Is the material abrasive? Is it combustible? And are there any chemical compatibility issues with convey hose, gaskets, filters, even in the material construction of the equipment? Does your material look like smoke? That picture in the upper left is talcum powder. It does have such a high fines content that you need more filter area for a product like that. The picture in the middle shows a material that we would consider non-free flowing, has very high angle of repose, and would require a lot of considerations in the receiver design and the discharge valve. You see the picture on the right, the materials come in all shapes and sizes and characteristics. How do you receive the raw materials into your plant? How is it going to be introduced into the process? Because there are different ways of introducing it into a vacuum conveying system, some more manual than others, some more suitable to automation than others, and some easier to control the dust factor. So your material might come in paper bags, barber drums and barrels, bulk bags, also known as super sacks, RIBCs, or bulk boxes. They may be supplied from a silo or a large day bin. They may come from rail cars, and they may also come from an upstream process equipment, which is now you need to know everything about the upstream process. Picture on the left shows bulk bag unloaders, where numerous different ingredients are introduced into a vacuum convey line that runs underneath. And this plant is set up for fast change out of bags. And the material is conveyed up into receivers that are on load cells, so they know exactly how much they're conveying into the process. But the bulk bag allows you to discharge to go through 2,000 pounds of material in a hurry, or to run smaller batches and stop in the middle. The picture on the right shows a bag dump station. So if your material is coming in craft bags or plastic bags, and they need to be manually dumped into the process, the bag dump station, in this case, has integral dust collection. So it draws material away from the operator and keeps the dusting down when the bag is being cut open and dumped. And with the vacuum conveying system, material is always drawn into the bag dump station. The sixth point that we have is what is the upstream process that might be supplying the material? Is it coming from a feeder of one type, or a mixer, an extruder hopper, reactors, other types of equipment, screw conveyors, heated vessels, chilled vessels? All of them affect the conveying process that we're talking about today. You need to know everything about the frequency of the material coming out of it. Does it come out as a discharge as a batch? Is it discharged continually? And how is it going to behave when it comes out of that process? Headroom. This is in installing equipment in existing plants. This is often one of the more difficult things to work with. Existing process equipment, when it was originally installed, might have been designed for screw conveyors or manual dumping, and now the need is to install vacuum conveying equipment above it, and headroom is always dear. We generally say that even the smallest conveying system for a powder will require at least 30 inches of headroom over your process. And this takes into account maintenance requirements for filter access, being able to inspect discharge valves, and to be able to access the equipment below the conveyor. We also refer to being in over our head. Sometimes the rate required does not work with the headroom that's available, and there are a few ways of dealing with that. One is using a filterless vacuum receiver, in which some carryover dust is allowed to pass through the receiver, and it's collected in another filtered vessel that might be at ground level, or it might be able to be suspended at a higher point near the process. But both of those ways allow us to collect the carryover dust. It's not lost product, but sometimes you have to, it does add hardware to the scope of work. Scaling valves or occasionally a positive pressure system might be the only other choices. The type of operation that you are feeding needs to be known. You need to know whether you're going to receive a batch of material in that process, such as a feeder or an intermediate hopper. The picture on the right shows some small conveyors that are discharging into a surge bin. So that's a batch process. Other receivers might use rotary valves to meter the material into the process, which can be considered continuous conveying, or you can convey the material into the receiver and at the end of the convey cycle then discharge it in a metered way. Some process can't take the surge of material coming out in one batch. There's also some processes like the loss and weight feeders in the plastics industry. They have unique ways of being fed. Other design considerations include your geographic or atmospheric conditions. Altitude plays a big part in sizing a system. The higher the altitude, the more air is required to convey the material. The electrical factors, which generally refer to 50 hertz versus 60 hertz. If you're transplanting a factory, a production facility to another country, You can't necessarily duplicate the equipment if it's running on 50 hertz. Plant conditions is the plant temperature controlled. Throughput of certain powders that are moisture absorbing can have flow problems or discharge problems on humid days if your plant is not temperature controlled. Materials of construction. This is a product contact question generally. Carbon steel with various types of coatings is the baseline. Generally, we're talking about all metallic construction. I'm not aware of anyone using plastic materials of construction, primarily for static control reasons and contamination reasons, where the plastic might wear. And for that same reason, some customers may want stainless steel construction instead of carbon steel because they don't have to worry about coatings coming off. It depends on the level of purity and quality that needs to be maintained. In the food grade or the medical grade plastics industry, stainless steel is the choice, either 304 or 316L. The level of polish is also specified for ease of cleanliness and again for to avoid contamination that might be left over on irregular or rough surfaces. And who cares about the material of construction? Actually, the maintenance people and the QC, the quality control people, care deeply about material of construction. In some industries, I mentioned the ability of a product to wear off of, for a coating, to wear off of a receiver can affect the quality of the product that's being produced. Some materials are abrasive over time, and the durability of the equipment, the abrasion-resistant factors do matter. And if the equipment needs to be cleaned, the maintenance people would be very happy to know that there are no glued-in gaskets, that all the welds are ground smooth. In the case of food grade or medical plastics, that the equipment is passivated to remove impurities. These are some of the standards that come into the material of construction, and they can greatly affect the cost of the equipment. Some of the basic components of a vacuum conveying system, we start at the beginning, just like the Google locate me button, or the people from National Lampoon's Vacation. They have to start. So depending on what your material comes in, you might be using wands. If your material comes in a barrel or a drum, or even in some cases bags for minor ingredients, your operator will use a wand. And it does require operator manipulation generally to keep the material flowing to the wand. It works very well for minor ingredients, but it does require labor. Feed bins are another way of introducing material into the conveying system. They work really well for mixer output or grinder output, where they can hold a volume of material, and when the conveying system goes into convey mode, the material is available for in the feed bin. Bag dump stations, another operator-controlled operation, and there is a physical limit to how many bags an operator can generally handle in a day. Depends on the nature of the equipment and how long his day is. But bag dump stations are another way of introducing the material in a controlled way into a conveying system. And bulk bag unloaders work very well for automation and for higher rate system. When you're talking about systems that convey up to 20 or 25,000 pounds an hour, that's very difficult to achieve with manual bag dumping or unloading material from drums. So bulk bags or silos or day bins are the way to handle large rates. So this is just a time check. Want to see how everybody's doing, or everybody's still awake?
We're doing good, Dave.
There's an interim point on in the movie National Lampoon's Vacation. Everybody's still in good shape in the movie. So I hope you are as well. Everyone remembers kids in the back seat saying, "Are we there yet?" The next element of the basic components of a conveying system is whether you need rigid tubing or whether you're using flexible hose to bring material into the conveying system. Flexible hose would normally be on an operator-controlled, an operator-manipulated wand, either drawing material out of a box or a drum. That hose should be smooth bore on the inside, unlike a shop-type vacuum hose that has a lot of corrugations on the inside. You want a hose that is smooth, not only for cleanliness, but for performance. No material won't build up if it has no corrugations. It should be a static grounded hose. The movement of any powders by air or pellets by air will generate static electricity. And there is an operator comfort factor there, as well as a combustible dust prevention or combustion prevention factor with the grounding of the hose. If you're doing food grade plastics, then the hose should likewise be constructed of a food grade material, an FDA approved food grade plastic for urethane. Hoses as well as tubing should be smooth bore, sweep elbows, meaning long radius elbows, couplings that allow for ease of disassembly and inspection. Occasionally, some materials that are sticky or they smear or they are abrasive, abrasion-resistant hose makes an excellent substitution for a metal elbow. A flexible hose keeps material that has a tendency to stick, it keeps it from sticking because it's got a little bit of liveliness to it. It moves and flexes and causes material to bounce off of it rather than taking the impact like a metal elbow. Metallic tubing, it's generally either aluminum or stainless steel. Please no plastic pipe to transfer material. The static electricity and the flow characteristics generally make plastic pipe non-indicative for conveying of powders. In a larger conveying system where the vacuum producer is separated from the filter separator, you can use aluminum tubing because it's generally a clear air, no debris passing through that tubing. Different types of receivers. This is your destination, or at least your intermediate destination before it gets into the process. We call them filter receivers or filter separators. The conical discharge is the common design, and generally for powders, it will be a 60-degree or a 70-degree cone, nothing less than that. Pellets might flow out of a more shallow cone, but in the powder industry, 60 degrees minimum, 70 degrees desirable, and that factor, that may come down to a headroom decision as well. If you have the headroom available, 70 degrees always works better. There is another type of receiver that we refer to as a tube hopper. which is essentially a straight-sided cone. It has no shoulders. It is a cylinder with a full opening valve, and that's used for products, non-free-flowing powders. Perhaps pigments might be one of the products in that category, or a material that does absorb moisture, or materials that de-aerate readily when they reach the receiver. If they settle and the air is forced out, a straight-sided receiver will get the material, will allow the material to discharge. Occasionally you have to add other devices to get material to come out, such as aeration, occasionally vibration, or live bottom bins. The vacuum producer. There is no vacuum producer that fits all. I think that's a fair statement. The Venturi is a great choice for a vacuum producer from a couple of different reasons. It's simple. It has no moving parts. It runs on compressed air instead of electricity. And there are no moving parts. So it is excellent for rates generally up to 3,000 pounds an hour, depending on the type of material that's being conveyed. It is an excellent choice for hazardous environments because of you can make it a completely non-electrical operation from controls, from a control standpoint. And it is an excellent choice for intermittent applications, small for minors or medium convey rates, again up to 3,000 pounds an hour. In some plants, compressed air is a highly valued commodity, but compared to the purchase cost, it actually has a lower upfront capital cost, which can change people's minds about whether they want to use compressed air or not. A regenerative blower is a middle-of-the-road vacuum producer. It has a good combination of vacuum and airflow, and it makes it a good choice for a vacuum producer for some powders, for pellets and granules, at medium distances. Depending on the type of material, you might be able to go 40 feet horizontal. And a decent vertical lift, and again in a conveying range that might be in the several thousand pound, 5,000 pound range. They operate on their continuous duty. They are generally running on 3-phase. Some smaller systems will run on single-phase electricity, but they are a centrifugal type of vacuum producer. The impeller is directly coupled to the motor in most cases. They're also nice from a noise level. They have a nice medium, a nice palatable noise level. Positive displacement vacuum pumps are probably the closest thing to being a universal vacuum producer, meaning they could do just about any job, but for many jobs they would be overkill. 3 horsepower is the low end for most vacuum pumps, going up into, from a vacuum conveying system, 50, 60 horsepower. But if you only need 1,000 pounds an hour on a short distance, then the Venturi or even a regen blower is maybe a more practical choice. On the other hand, a PD pump would be able to do the job without any trouble. It just might be overkill. But a PD pump is a different type of vacuum producer. It does not have much of a downward slope. When the work gets hard, a PD pump works harder. So they will operate at vacuum levels in the 12 to 16 inches of mercury category, compared to a regen blower that might operate in the 4, 5, 6 inches of mercury range typically. along with airflow. PD pumps also with belt-driven arrangements make them well suited for different electrical requirements, custom motors, hazardous location motors, much more suitable than a regen blower, which has they're supplied with motors generally, and they're more difficult to specialize or to customize. Basic components, controls. They can range from an air-powered vacuum, which is has very simple controls, solenoid operated, on, off, and can run on single-phase electricity if needed, or just on compressed air. Automation and communication are definitely the trends these days for preventive maintenance, for automation for reducing direct labor to observe the equipment, and to avoid failures of the equipment. So we definitely see a lot more controls that are connected through the Ethernet, through DCS systems in larger facilities, and or standalone. There are local control panels that may have their own PLCs in them, or the larger controlled systems that where the conveying system is a slave to controls in the DCS system. You definitely need to know your area classification, because this is one of those areas that has great effect on costs, as well as safety and compliance. The lungs of a pneumatic conveying system are the filters. If the lungs don't function well, then the rest of the system will function poorly as well, in an unhealthy way, you might say. Determining the right air-to-cloth ratio, the amount to go with the amount of airflow that's being generated in the system. It's measured in terms of square feet, and when you compare the airflow of the system to the surface area of the filters, you end up with a factor known as the air-to-cloth ratio. And the lower the air-to-cloth ratio, for example, 2-to-1 or 4-to-1, the system will be working less strenuously than a system that has a 10-to-1 or 12-to-1 air-to-cloth ratio. So there is an energy efficiency, a filter efficiency. The filters are more efficient at lower air-to-cloth ratio. Can velocity is another factor. You can have a receiver with a lot of filters, but if there's not enough room for the materials, the powders, to fall out of the airstream, then you have a can velocity problem. Can velocity, you might also describe it as a tempest in a teapot, but you basically have too much activity going on, powders not settling out of the airstream because the vessel is too small. So along with filter area, an appropriate diameter receiver needs to be calculated. And the interstitial velocity is another fancy word for the speed of the powder, speed of the airflow in between the filters. If you make the filters too crowded together, then the speed between the airflow through the filters is too high, and they won't clean very well. Different types of filtration. Sock-type filters are shown in that picture. That filter would have an internal cage. They are excellent for materials that are sticky or that are fibrous. Because of the smooth surface, the Teflon-coated filters will release the material very well. And then you have a choice of either today's technology. You have a choice of either a static conductive Teflon filter or spun bond polyester. those two acronyms shown there, and they both have excellent powder release characteristics. Static conductive is more the standard these days than non-static conductive. There are some groups that feel that non-static conductive is safer, but there are two schools of thought about that. The other choice for sock type filters are pleated bags, which fit the same diameter of a tube sheet, but they give a lot more filter area. In general, you could say that a pleated filter has 5 times more filter area than a sock type. Now, pleated filters are different than cartridges. Cartridges have a much tighter pleat count, and a pleated bag might only have a 1-inch deep pleat, whereas a cartridge filter, and maybe a 1/2-inch spacing between the pleats, whereas a cartridge filter might have a 1/4 of an inch or a 1/2 an inch space and a much deeper pleat, which means it doesn't release powders as well. One new type of filter that's on the market shown on the left where there is no end cap. So if your material likes to build up in the end cap, this type of filter really is a very clean design. Filter access and maintenance. This is part of the dust consideration as well. We see a lot more opportunities for what we call swing away covers, where operators want to remove the filters from the clean side of the filter plate. This, compared to the picture on the right, if it's a larger receiver, the receiver with doors requires an operator to put part of his body in it, whether it's a leg or an arm or a head, while he's changing filters. And this can run into confined space concerns and air quality permit or non-permit required confined spaces. It is very nice on the operators to be able to remove the filters from the top side of the filter, from the clean side of the filter plate. Types of conveying systems for loss and weight feeders. There are convey on demand and discharge on demand are the two general categories. In convey and on demand, when the feeder calls for material, it sends a signal to the conveyor, at which point it transports material and delivers it to the loss and weight feeder. The signal that causes this is usually a level control or a control element of the feeder. In this system, there is a slight delay. The conveyor the feeder has to call for material before it's totally empty. Discharge on demand is a concept where the receiver is always full of material, so that when the loss and weight feeder calls for material, it simply opens the discharge gate and drops the material into the feeder. There is no loss of timing for delivering more material. And then the receiver will then refill itself and hold material until it is called for again. So this is a high productivity and less of a chance of running out of material. One of the questions that everyone likes to ask is, how do I figure out the cost of a conveying system? I would love to provide numbers to answer that, but due to the variety of processes and powders and distances and all the factors that we've been talking about, it's difficult to put numbers on it. But I can tell you that the convey rate is the first major factor. We mentioned before, if you need 2,000 pounds over the course of 1 hour to satisfy your process, you'll have one system. If you need 2,000 pounds, but you need it all in a 5-minute span, you have just multiplied the size of your system by a factor of 12. The distance from the pickup point to the discharge point is a huge factor. If you were to look at for example, an ABS resin material that weighs approximately 20 pounds a cubic foot. At 30-foot distance, you'll be transferring more material. If you were to extend that distance to 200 feet, your rate drops to about 25% of the original. So the same rate, but at 200-foot distance is now you need to increase the size of your system by a factor of 4. The electrical classification, which deals mostly with controls and motors, if you're able to move the vacuum producer to an unclassified area or to have the controls in an unclassified area, you can save some good capital money as opposed to requiring potentially explosion-proof controls. The overhead space, if you have the overhead space, it's better to have the filters on top of the process. If you have to remove it to the ground level, then you will have some more hardware to add to the process. Automation and or communication might be a higher upfront cost, but may save a lot of money over the course of the lifespan of the equipment and from a preventive maintenance standpoint. Material handling, if you're able to move to larger incoming material containers such as bulk bags, then generally you'll reduce the cost of your raw material, and if it suits your process, it allows you to get higher rates of conveying. Accuracy, whether you need load cells or not, adds to the cost, and then elevation, which increases the cost of the size of the system if you're at a higher elevation. Last but not least, we strongly recommend that you have your materials tested in a similar application, a full scale test. One company may have a fumed silica powder that behaves one way and has one characteristics, but the next man who says he also has fumed silica may have totally different characteristics. So even though a company may say they have experience in handling a certain product, we highly recommend full-scale testing. There was a statistic that said 70% of bulk powder process new installations have cost overruns, and generally it's because the material is not being tested before the equipment's being installed. And your goal is to make extruded parts or plastic, in general, plastic parts. The last thing you want to do is tinker with or mess with the system that gets the powder to your process. Make sure that your supplier understands your goals. And just like all good journeys, they come to an end. National Lampoon, they needed to get to Wally World. So we've reached our Wally World, and that feels good. So at this time, I think we're ready for questions. Jim?
Thanks, David. I'm back on. We have a few minutes for questions, and a couple have come in. Let's start off with this one. What SOx are required in the receiving bin for submicron particles? Our vacuum maxes out each cycle, and I'm thinking the SOx are clogging up.
That is a possible conclusion. There are a couple of ways of addressing a problem like that. Well, first you need to know what the filter media efficiency is. If it's a Teflon-coated filter media, its nominal rating is 99.9% efficient at 1 micron. That's a nominal answer. But that is based on a certain amount of airflow going through a square foot of filter. If you have If the filters are undersized, meaning there's not enough filter area, square feet, then you may be trying to pull too much air through that filter and they will blind. So that is one possible cause. Another possible cause is that the can velocity is too high. You're pulling too much airflow for the size of the receiver, and the powder just immediately goes up to the filters. So you are blinding the filters. They both have different resolutions. The first one, you can change sock type filters to pleated bags. They generally fit the same filter plate, or with small modifications you can put in and get that much more filter area in your same receiver. The other question is that someone may have increased the airflow, increased the performance of the system where you've just got too much airflow, and the only solution is either a bigger receiver or to slow down the vacuum process. There are some other smaller factors that are in that, but that's one possible answer.
Okay. My powder is a combustible dust. Do I have to design explosion protection on the receiver?
NFPA has the opinion that a pneumatic conveying system is probably the easiest to protect in a process hazards analysis. It's the easiest to protect because your source of powder is generally pure, meaning there's no trapped metal in it. The conveying lines in the receivers are generally stainless steel construction, which is anti-sparking by nature, and your filters are static conductive. So in a process hazards analysis, you've probably eliminated, but you have to ground everything, static grounded. But in general, you could say that they are low on the risk scale. But that is, ultimately, can only be answered by the insurance company, your insurance carrier, and the authority having local jurisdiction, which might be a fire marshal or your own safety people. But NFPA does allow pneumatic conveying equipment with the right evaluation to not require explosion protection. Some companies will say they'd rather have the belt and suspenders, and they'll put explosion venting or chemical suppression on the system simply because they don't want to fall back on the rules if they had some reason to believe that they should have protected the receiver. Okay.
This next question is more about pellets, but I'll ask it anyway. I'm feeding 150 C regrind pellets and seeing a lot of angel hair. What about replacing the elbows with 90-degree pipes or flexible tubing?
There are, angel hair is kind of a nature of the beast with plastic pellets, especially if they're somewhat soft. But there are elbows that are designed specifically for plastic pellet conveying to reduce angel hair. There are some suppliers out there that are advertising that promotion. Abrasion-resistant hose might be a factor, but 150 degrees C is is an elevated temperature, and most plastic or elastomers are not going to stand up to that temperature over time. So I think that maybe my recommendation would be to look for those elbows that are designed specifically to eliminate angel hair.
Right. What is the maximum distance for a vacuum conveying system?
Depending on the material, the general answer, we would say maybe 300 feet. And that's a very general answer. With the right materials, you can go 400 or 500 feet, but if you have a reasonable rate to attain, it's just that the further you go between the pickup point and the destination, the more air you need at the pickup point and less material. So as I was talking about before, if you move from 30 feet to 200 feet for a given material, you now have to upsize the system by a factor of 4. So there is probably a place where you have diminishing returns at 300 feet or beyond, where you may need to look at another technology.
Okay. Can you comment under what conditions you would use different vacuum producers, such as Venturi, regeneration blower, or positive displacement pump?
If in the plastics industry, I would say if it's an explosion hazard area, my first choice would be the Venturi operated system, because it has a much lower capital cost. It has much lower maintenance. So I would pick a Venturi, and again, they are best when you're in the up and in, or in the let's say 20 feet by 20 feet horizontal and vertical category, and rates up to maybe 3,000 pounds an hour. The regen blowers are middle of the road. They are usually outweighed by PD pumps, because PD pumps have a great long lifespan. They work for decades, and they have absolutely no problems in meeting rates. They're very reliable. So longer distances, heavier loads, PD pumps I'm speaking of now, longer distances or heavier loads or higher density materials, not applicable to this industry, but when you handle metal powders, PD pumps, you start with PD pumps because they can handle those harder jobs.
Okay, thank you, David. I think we've run through our questions. I'd like to thank David for his informative presentation this afternoon, and I'd also like to thank all attendees for their interaction and their questions. This webinar was recorded, and soon all attendees will be receiving an email with a link to the recorded version on our website, ptonline.com. Please feel free to share that link with any of your colleagues who could not join us today. Thank you very much. This concludes our webinar.